Hello everyone, in this lecture video we are going to look at 4 examples of BCA stoichiometry. We're going to jump right in with our first example, which is a picture example. We're provided with the reaction equation 2Na plus Cl2 reacts to form 2NaCl, and we're also provided with a before particle picture. And we have been told that we need to draw the after particle picture, and we're going to also draw a BCA table. So our product in this reaction equation is sodium chloride, NaCl. So I'm going to go ahead and get started by drawing a sodium chloride molecule in the after box. I find it helpful when I'm doing pictures like this to cross out the reactant atoms as I draw them in my after picture, just so that I keep track of how many atoms I have to work with and what I've already used up. So I draw my first sodium chloride molecule, and I am not anywhere near done, so I'm going to draw a second one. When I draw my second sodium chloride molecule, I notice that I have crossed out all of the sodium atoms from the before picture. So I can't draw any more sodium chloride molecules. I've run out of sodium to make sodium chloride. But I do have this leftover chlorine molecule, and conservation of mass says the atoms can't just appear or disappear. We have to keep track of them. So we are going to go ahead and show it in our after box as a chlorine molecule. When we make our BCA table, we're going to have a column for every substance in the chemical reaction equation. So a column for sodium, a column for chlorine, and a column for sodium chloride. We have a before row that matches our before picture, 2 sodium atoms floating around, 2 chlorine molecules, and no sodium chloride molecules yet. We have an after row that matches our after picture, no leftover sodium atoms floating around by themselves, 1 chlorine molecule left over, and 2 new molecules of sodium chloride that were produced by the chemical reaction. I kind of just go back and map in the change row from my after picture. So there's no more sodium, but we started with 2, which means we had to have used up 2. We start with 2 chlorine, we end with 1, so that means we had to use up 1. We start with no sodium chloride, but we end with 2, so that means we would have to make 2 more. I've also marked on my BCA table the limiting reactant. In this case, that is sodium. The limiting reactant is the reactant that you run out of, that limits your ability to make more. And in this case, that was sodium. Also notice that you should have 0 of your limiting reactant left over in your after row. And sodium has no leftover in the after row. Moving on to example 2, we have a new chemical reaction equation. 4K plus O2 yields 2K2O. We have a new before picture. And so we're going to proceed in the same manner by starting to draw our product molecules and crossing out the reactant atoms as we use them up. So we get 2 molecules of K2O before we run out of potassium, and we have a leftover oxygen molecule hanging around in our container. So in our BCA table, we are going to mark potassium as the limiting reactant because that is the reactant that we've run out of. There's none of it left over. And we have some leftover oxygen, a leftover oxygen molecule. Now we're going to turn to a numerical example. Here we have a problem. Given the following reaction, CH4 plus 2O2 yields CO2 plus 2H2O, how many grams of CO2 will be produced from 12 grams of CH4 and 133 grams of O2? Here I need to make a very important statement. The only numbers that go into a BCA table must be moles. You may only put moles into your BCA table. So before we start putting in 12 grams and 133 grams, we have to change those numbers from grams into moles because they must be in moles to go in to the BCA table. So I'm going to get out my periodic table. I'm going to look up the masses of these elements, and I'm going to set up some railroad tracks to convert 12 grams of CH4 into moles of CH4 and 133 grams of oxygen into moles of oxygen. When I do that, I get 0.748 moles of CH4 and 4.16 moles of oxygen. Previously, in our pictorial problems, we identified the limiting reactant as the reactant that you ran out of. But it is much trickier to do that on a numerical problem because it is not always the reactant that you have less of, as we saw in our potassium oxide problem. So how do we do that in a numerical problem? In a numerical problem, we identify the limiting reactant using something called reaction equivalence. And the reactant with the fewest number of reaction equivalents is the limiting reactant. The reaction equivalence is a number. We calculate that number by taking the number of moles in the before row and dividing it by the coefficient from the balanced chemical reaction equation. So the reaction equivalent combines number of moles and the reaction equation. So in our example, we are going to take our number of before moles for CH4, 0.748, and we're going to divide it by the coefficient of CH4 in the balanced chemical reaction equation, which would be 1. And so 0.748 divided by 1 is going to be 0.748. We're going to take our 4.16 moles of oxygen and divide that by the coefficient for oxygen, which was 2. So that would be 2.08. In this case, CH4 is our limiting reactant because it has the smallest number of reaction equivalents, which means that we're going to run out of CH4 before we run out of oxygen. Once you've marked methane, CH4, as your limiting reactant, you are now ready to proceed with the rest of the problem. So you always start your railroad tracks with the limiting reactant, in this case CH4. So just like our more simple stoichiometry that we learned previously, we're going to use a mole-mole ratio from the balanced chemical reaction equation. The coefficient for CO2 is 1. The coefficient for CH4 is 1. So that's 1 mole to 1 mole. We are going to use the molar mass of CO2 to get our answer into grams of CO2. And that answer should be 32.9 grams of CO2. You may have noticed that there are still some blank spots in our BCA table. There's also no A in our BCA table. So in order to go ahead and fill out the rest of the table, we're going to use other mole-mole ratios from the balanced chemical reaction equation to determine the amounts of the other substances. Again, all of these railroad tracks start with the limiting reactant. Once we've done that, we can use some simple addition and subtraction to determine the values of the after row. Again, notice that the amount of limiting reactant left over is 0, and we have no negative afters. Again, negative afters would be a sign that you did something wrong somewhere in your math or made a mistake identifying the limiting reactant. Our final example says, given the following reaction, copper plus silver nitrate reacts to form silver and copper nitrate, how many grams of silver will be produced from 19 grams of copper and 125 grams of silver nitrate? Again, all of the numbers in your table must be in moles. So we go to the periodic table, we look up the masses of the elements involved, we set up railroad tracks to convert the masses given in the problem to moles. 19 grams of copper, there are 63.55 grams of copper in a mole, gives us 0.299 moles of copper, and we can put that into our table. Added up the mass of silver nitrate, got 169.88. We got 125 grams of it. That gives us 0.736 moles of silver nitrate. Notice that there are 0 moles of our products in the beginning of our table, right? Silver and copper nitrate are what we are making in this reaction. So there is none in the reacting container before we start. Our next step, once we have the before row filled in, is to identify our limiting reactant. We do that using reaction equivalence. So we take the number of moles before for copper, 0.299. We divide it by the coefficient for copper, 1, from the reaction equation, and that gives us 0.299 reaction equivalence for copper. We do the same process for the silver nitrate. The coefficient is 2 instead of 1. And that gives us 0.368 reaction equivalents for silver nitrate. Copper has fewer reaction equivalents than silver nitrate, so that means we are going to run out of the copper before we run out of the silver nitrate. So we mark copper as our limiting reactant. Once we've done that, we can use copper to identify the change values for the other substances in the table. All of our railroad tracks start with copper because that is our limiting reactant. And then we use mole-mole ratios from the balanced chemical reaction equation to determine the change values for the other substances. Once we've done that, we use simple addition and subtraction to figure out the after values for each substance. Again, notice no leftover limiting reactant and no negative after values. If you get a negative after value, you messed up somewhere. Go back and change it. Now the problem asked us specifically for the grams of silver. So we would need to go to the periodic table and look up the molar mass of silver, add it to our railroad tracks for silver, and that will tell us that there should be 64.5 grams of silver coming out of this reaction container. That's all for today. We looked at 4 examples of BCA stoichiometry, including 2 picture examples and 2 numerical examples. Thank you very much and have a nice day.